Welcome to the third lecture from chapter number 9. We will continue studying pseudo and MOS logic. In our early lectures we studied that a pseudo and MOS structure, the structure of a pseudo and MOS gate is that the nMOS array is the same as we have in case of CMOS, but the PMOS array is replaced with a single transistor that is always on. So the problem is when we have the input voltage such that the output voltage has to be logic 0, we cannot achieve VOL exactly equal to 0 because the both arrays are on. So there is a voltage drop across here and a voltage drop across this transistor, so we get a VOL that is greater than 0. In our last lecture we studied the mathematical equation of VOL for a NOT. In this lecture we will study mathematical equations for NAND 2 and NOR 2, and I'll give you homework at the end. A NAND 2 can be represented such a way that the nMOS array is the same as we have in a regular CMOS circuit, but the PMOS, there is only one PMOS and it's always on. So if we have two transistors, each of them has been taken from a NOT. It's equivalent to the nMOS that we used in case of NOT. Then we have the total resistance doubled because now we have two transistors here, so the total resistance is doubled. This means beta n, which is inversely proportional to resistance, is half compared to NOT, because beta is inversely proportional to resistance, or resistance is inversely proportional to beta, so beta is half. And in case of NOT we studied that this is the equation when we have one PMOS and one nMOS and one PMOS. That was in case of a NOT that we studied in last lecture. In this lecture we have these two transistors instead of a single transistor that we had in case of NOT. So what we have to do, we have to take the cumulative effect, and that is beta n is half because resistance is doubled. So what should we do? We should divide it by 2. Now we will solve as we solved in our last lecture, and we will reach to an expression VOL, solving in the same way as we did in our last lecture. We'll reach VOL is VDD minus VTN minus VDD minus VTN squared minus beta P over beta N VTD minus VTP squared, and this whole is under a square root, right? So now we have beta n by 2 instead of beta n, so we'll write it beta n by 2, or we can simply write this 2 in numerator. So now how would you compare this VOL that we have written for NAND 2? How would you compare this with the VOL of NOT? How would you do that? Yes, we can compare it because this term is doubled. This means if this term is increased, let me use blue pen is increased, this quantity is the same, so the quantity that is being subtracted is increased. This means the overall quantity, this overall that is in the square root, would be decreased. If this quantity is decreased, this quantity is the same, so the quantity that is being subtracted out of this is decreased. This means now the net effect would be increased, so VOL would be increased. So VOL in case of NAND 2 would be greater than the VOL that we achieved in case of a NOT. This means there is a disadvantage. Now we have a reduced VOL compared to the VOL that we had in case of a NOT. So that we have an increased VOL. Increased VOL is not good. Yes, increased VOL increased VOL isn't good. We should have a small VOL, and ideally VOL should be 0. That is the case when we have VOL is equal to 0 in case of CMOS. So for this circuit we have an increased VOL compared to the VOL that we had in case of a NOT, which is not good. Right, let's move on to the other circuit that we have planned for today is the pseudo NMOS NOR2. The difference between this and the NOR2 would be this PMOS array remains the same, the output capacitance remains the same, except that we have these two transistors in parallel instead of being in series. Now we have these two transistors in parallel. So this is the difference. This is pseudo NMOS NOR2. Right, now this joint beta n is not half compared to NOT. What is it? Now we have two transistors, they both are in parallel, and each of them has a beta that is beta n and beta n, and they're in parallel, so total beta n will be beta n by 2. Right, so total resistance would be R by 2. I'm sorry, total resistance would be R by 2. The total resistance is R by 2, and beta n is inversely proportional to resistance. So if resistance is half, the term that is opposite, that is inversely proportional to resistance, would be doubled. So now the joint beta n is double in case of NOR2, because now we have two resistors in parallel. The resistance is half, beta is doubled, because beta is a quantity that is inversely proportional to resistance. So instead of by 2 here, we'll have a term that is 2 times beta. So we'll not cancel this 2 with this 2, because we want to cancel this 2 with this 2. So this beta n is replaced with 2 beta n, and this 2 appears here. This 2 appears here. And let's see what is the effect, and how can we compare this VOL with the VOL of NOT. Now we have a term that is double but in the numerator. This means what happens to this? Of course this will be decreased, because now we are dividing this whole term by 2. This means, let me use blue pen, this whole term would be decreased. What's about the term that is in under the square root? This would be increased, because this term is constant. The term being subtracted is decreased. This means the overall difference, if this term is being subtracted, is decreased, so the overall difference would be increased. And if it is increased, what happens to VOL? This term is the same. The term being subtracted is decreased. Sorry, the term being subtracted is increased. So what happens to the net? What happens to the net difference? The term being subtracted is increased. So what happens to the net difference? Of course, it will be decreased. So VOL for node 2 would be smaller than the VOL. So this is decreased, and decreased VOL is good, because decreased VOL takes us to a value that is closer to 0, and it should ideally be exactly equal to 0. So for node 2 we get a better VOL. So we got a VOL for NOT, and then we got a VOL for NAND 2 that was a VOL higher than that of NOT, and now we have derived an expression of VOL for NOT 2 which is smaller than the VOL of NOT. So now there is a homework for my students, and it's only a one-line homework. Homework is arrange, adjust aspect ratios of the NMOS transistors we are using, adjust those aspect ratios so that to make VOL of NAND 2 equal to VOL of NOR 2 is equal to VOL of NOT. So this is your homework. You have to arrange aspect ratios so that all these VOLs are the same and they must be equal to the VOL of NOT, right? So that's all for today's lecture. We will continue studying high speed logic in our upcoming lectures. Thank you.